Swayam Prabha. Digital India. Educated India.
Alright, so we move on to the third presentation of the session. The third one and the next one are both virtual presentations. In the sense, unfortunately, the speaker is not being able to come here. Our next presentation is, hopefully I'm pronouncing this correctly, Jai Cheng Jeng from NTU, National Taipei University of Technology. And he's going to present. So the topic is database tuning of IPD controllers for time-delayed unstable processes considering output performance, control effort, and robustness. Hope the speaker is able to hear us.
Good afternoon, everyone, and welcome to my presentation. First of all, thank you all for coming here today. I'm glad to see you. My name is Poramet Buddhiwong. Today, I would like to talk about database tuning or PID controller for time delay unstable processes, considering output performance, control effort, and robustness. Sorry. My presentation is divided into 5 parts: research background, the proposed IPD tuning method, procedure for controller tuning, simulation example, and conclusion. First, I would like to give you some background information in research background. Let's start with the IPD controller. As you know, IPD controller is widely used in chemical process industry because IPD controller have a simple structure and perform satisfactorily in many control applications. However, PID controller perform badly for the controlling time delay unstable processes. The major weakness of the basic PID controller are the effect of the proportional kick and derivative kick. In order to minimize this effect, modified form of the control structure have been proposed, such as a PIDP and PIPD controller. But the major weakness of the PIDP and PIPD structure is they have 4 parameters to be adjusted. So it should be difficult to decide. And from the problem that I mentioned before, IPD controller have been proposed. IPD controller is one of the modified version of the PID controller. It was proposed for eliminating the proportional and derivative kick. In the right-hand side of this slide, show the IPD controller structure, and the bottom of this slide show the control output equation of PID and IPD controller. As you can see from the equation, all term of the PID controller respond on the error signal, but the IPD controller have only I term respond on the error signal, and PD term work on the process output. After we know that what is the IPD controller, next I will talk about the proposed PID tuning method. In this work, the virtual reference feedback tuning framework is used to tune the controller. The main concept of the virtual reference feedback tuning is the finding the controller parameter that minimize the differential between the collected data and calculated data. Then this method requires the process data collected from the experiment under the closed loop operation. For for IPD controller, the virtual control output is calculated by use this equation and repeats the set point R with the process output Y multiplied by inverse reference model and rearrange this equation. For the reference model, there are two unknown parameters, theta and lambda. Theta has been defined and lambda has been found from the lambda which can achieve the target MS. After getting the reference model, we find the controller parameter that can minimize the differential between collected data output, collected controller output and the virtual controller output by the equation 1, and equation 1 can be solved by least square method as shown in the bottom of this slide. And after getting the set of the controller parameter Kc tau I tau d, we will find the optimal control parameter by changing the data in the reference model. The objective function of this work is a summation of control performance and output performance and control effort by using ISTE to estimate the output performance and ISCR for control efforts. Moreover, in our objective function have a eta as the trade-off parameter that trade-off between the output performance and controller effort. This slide shows the equation that's used to calculate the ISTE. Start from Euler E and substitute R equal to 1 divided by S. Because this method is designed based on the set point tagging, then derivative this equation, get this equation and put into this equation. And this slide shows the equation that's used to calculate ISDR for control efforts. Next, I will summarize the procedure for IPD tuning. Talking about the procedure for IPD tuning, I divide the procedure for IPD tuning into 4 parts. Step 1, collect the process data, input data, and output data from a closed loop search point test. And step 2, set the searching length of data and decide level of system robustness in terms of MS. And step 3, solve this minimization problem within the range of data that we define in step 2. The algorithm involves 2 nested iterative loops, inner loop and outer loop for the iteration lambda and theta respectively. For each chosen data, the parameter lambda have been found from the lambda which can achieve the target MS that we define in the step 2. And this procedure is repeat for order value of data until we get the minimum objective function. And step 3, use the data optimum from step 3 to obtain the proposed tuning parameter of the IPD controller. And next, I will talk about a simulation example. For the simulation example, in this work, compare the result with the model-based tuning design method. And because our time is limited, I will show the only two examples. In first example, consider the unstable second order past test time in this slide. I tune the controller by follow the tuning procedure in previous part. Sorry. And set the length of data equal to 0.5 to 1 and set the MS value equal to 5. That's lower than the calculated value from the reference paper. And the result from the step 3 and step 4 that's shown in this slide. One of the advantages of the proposed method is allow the user to manage the trade-off between the output performance and require control efforts under the specific robustness level. The trade-off parameter eta is used to explain the control effort priority. Okay, this slide shows the closed loop response to a unit step input chain and disturbance inject into the system at 50 seconds. As you can see from the result in the table 2 and figure 6, the proposed method achieved a better performance and control effort than the model-based design method, with respect to both set point tagging and determinant rejection. In the example 2, consider the third order time delay unstable process. For the model-based method, require the remodeling to the unstable first order past test time before tuning. And for that database method, I do the same step and get the result that shown in this slide. The bottom of this slide shows the IPD controller setting for example 2. And this slide shows the closed loop response to unit step input chain and disturbance inject to the system at 60 seconds. The database method perform better than the model-based design method with respect to both set point tagging and determinant rejection. The database method give a smaller overshoot than the model-based method and can reduce the aggression in the control signal. And in this case, you can reduce the MS value for get better performance. For conclusion, we have developed the database method for IPD controller. Our method obtain the IPD setting directly using process data collected from a single experiment under the closed loop operation. This method contrasts with the model-based IPD tuning method that require accurate process model. Then the proposed method Then the proposed design procedure is simple and easy to implement. Moreover, the proposed design take robustness into the design parameter to meet the specification of the MS. And the effectiveness of the proposed method is apparent from the satisfactory control performance with respect to both set point tagging and disturbance rejection as shown in simulation example. Then the proposed method tuning is an effective alternative to existing the IPD controller design method. It's all for today. Thank you for your kind attention. And if you have any question and suggestion, please feel free to ask.
Thank you. We have time for a couple of questions. Yes.
Hello, yeah. So my question is, when you are saying you collect the data from closed loop operation, so that closed loop is using suboptimal tuning, or which, so it is not the tune controller which we use, right? Because when you collect the data from a closed loop operation, what do you mean, like under which controller it is working? So that is first. I have one follow-up question too. So when you compare against model-based decision, it can always depend upon the accuracy of the model. So you might also plot how your model predicts the data, because if I can improve the accuracy of the model, maybe that will match much closer with what I would get from the data-driven, the database control tool, right?
In first step, we can use the P controller, PID controller, PI controller. Is depend on the.
Yeah, so we get it. I suppose you are saying that there is option of using a P controller or a PI or PID depending on the process, right?
I mean, it's depend on all controller.
Okay. And okay. Does that answer your question at least partly? Okay. So the second question has to do with the accuracy of the model that you are using in model-based tuning. Is it correct? Yeah. So can you comment on how the accuracy of the model can affect the tuning of your IPD control? The question has to do with your model-based tuning. So you discussed a model-based tuning method. So the question, again I repeat, and of course if it doesn't work then perhaps you can communicate over email. It has to do with model-based tuning, okay? And it was a clear model-based method. So I think in the interest of time, we will not take up this question. I think for the same reason perhaps we will have to close the session because the speaker is facing issues in regards to communication. I think we'll stop here. Any questions that the audience may have, they will email you. Is it clear? Any further questions, the audience will send you by email. You may answer by email. Okay?
Okay.
Thank you very much. At this point in time, we will have to close this presentation. Thank you very much for joining us today. Thank you.